Kirchhoff's current and voltage laws. As we've already stated Kirchhoff's laws are the basis of circuit theory. So we'll individually look at each of these and then move on. So we're going to start off with Kirchhoff's current law. Which we typically define as KCL, and Kirchhoff's current law involves nodes. A node is also called a junction, is an equipotential surface where two or more elements connect. So what's going to be really important is that it's important to identify and count the number of nodes. So let's practice that. So imagine that we have these examples here. And so what we're really trying to do here is that we're going to ask the question, how many nodes are in the circuit? I typically use colors to help count the nodes. So let's do that. So let's say that we have this circuit. So if I look at this circuit here, I'm going to have a circuit that looks something like this. And now let's start looking at elements. That might look something like this. So if here are my elements, so now I have to highlight the number of nodes. So if I look at the number of nodes, I'm going to take a color. Let's say I take red, and if I isolate this equipotential or node, you'll see that that red represents 1. If I take this other one, the one on the bottom, and I highlight it with green, you could see that that represents a second node. And if I take the next color, that represents a third. And if I take another color, that represents 4. So we can see here is that this circuit has 4 nodes. And coloring really makes a difference here. Another circuit that we can do here is that we can also play this game here where we go, here's a node. And then let's say that I have another element here. Um, and then finally, here's my last node. So again, using a coloring scheme, by the way, I should have just come in here and labeled this. So this should have been 1. Then in this one, we call this 2. And this one, we call this 3. And here we call this 4. Let's try the same coloring scheme. So if I say, this is my red node, so everywhere where that wire is at gives me 1 node. Then if I go to a second one, let's go to this guy right here. You could see that this represents the second node. And then if I go to this guy right here, you could see that this represents the third node. And then finally, I could come in and add this last node. And even though this circuit is different, it has the same number of nodes. So once again, we can then say that this circuit has 4 nodes. So if I just come over here, I'm going to copy this. And then I'll just come over here and just say, this circuit has 4 nodes as well. So what does Kirchhoff's current law say about this? Which we lovingly call this KCL. It says that the algebraic sum of currents entering a node, let me be careful, entering any node is always 0. Now the sign convention, which we need to be able to talk about in order to identify how we write Kirchhoff's current law, essentially says that if I have a node here, then this is the current that's coming into that node. So what this tells us here is that this is a positive current. And therefore, we write this positive current with a plus I into the node. On the other hand, I could have a node that has current leaving the node. In other words, this current is coming out of the node. The sign convention says that this is a negative current, which means it assigns a negative sign for I out. So now, this is what KCL says here. KCL says that the algebraic sums of the currents coming in must equal the sum, or excuse me, minus the sum of outgoing currents must equal to 0. And I would say that this is how the vast majority of the people use it. So I'm going to call this the traditional way of stating KCL. However, note I can do an algebra where I bring the currents out. And I would say that this here, the current in, now equals the current out. Now, to me, this is the most useful form of KCL right here. And I would say that this right here is the way Carlos does. This is Carlos's way. And the reason why this is such a nice here is that this method of writing KCL implies that you never have a negative sign. In the traditional way, you do have a negative sign. So when I use KCL, I'm going to use this method right here. So here is KCL. You know, Carlos's way is not a new way. It's just one way that one could look at that. So let's look at an example here to show you what I mean. Example here, what we want to do here is that we want to apply KCL to these currents at this node. So when I look at this thing, here's what I see. I have a node, and then I'm going to arbitrarily pick currents. So I'm going to say that here's a current I1, and then I'm going to have 3 outgoing currents. So that means I'm going to have I2, I'm going to have I3, and I'm going to have current I4. By the way, I could have them the other direction too. So if you look at the traditional way, / books way, they pay attention to the signs. In other words, when they say the currents coming in, we look at what currents here are coming in, and then we subtract it from the currents coming out, and then we set that equal to 0. So I got to pay attention to the signs. So if I look at this, this is what we see. I'm going to see that the only current coming in is current I1. The rest of the currents are going out, which then means I have to subtract them. So here you could see that this is going to be I2 minus, and then I'm going to have 2 minus, and then the next one here is going to be I3, and then finally, I'm going to have I4, and that has to equal to 0. Now, this technique, what it does here is that you do have to pay to the signs. And furthermore, you're going to find here that you're going to have to do some algebra in many situations in order to look at the current that you're actually looking at here. So now what I want to go do here is that I want to look at Carlos's method. or Carlos's way includes no signs. All of the signs are positive. So instead of writing a sum, I typically say that this is the current in and this is the current out. So I dropped the sign convention, the summation sign. By the way, this is called Einstein's convention. So now when I look at this thing, here's what I see. I see that immediately I have current 1 coming in. And because I have current 1 coming in, I now come in and without looking at the signs, I now start to add these guys. So here I go. So this is going to be the current 2. This is going to be the current 3. And this is going to be the current 4. And you could see that mathematically, this is giving me the exact same answer as what we did before. The only difference here is that we didn't fuss about the sign. So, as I said before, signs are the killers in circuits. Okay, that's Kirchhoff's current law. Now, let's go look at Kirchhoff's voltage law. So here we go. Kirchhoff's voltage law, which we then lovingly called KVL, and loops. The E field is a conservative field or force, if you want to do that. And therefore, the work around a closed loop is always 0. That's what allows us to find a potential function. So then that means that the work of the E field is then the integral of the electric force along some displacement. This guy, as long as it's around a closed loop. And the way we typically write a closed loop is when we put a circle around our integral. This loop does not require that currents are passing through an element. And believe it or not, that is a really hard thing to learn. So this loop does not require that currents are passing through the elements. However, it's useful to imagine that current is following the chosen loop. So here we go. So we could now make a definition. The definition is a loop is any closed path formed within a circuit. So that's our definition of a loop. So let's look at an example to count the possible loops here. So it becomes super important to be able to count the number of loops. So here's our example. How many possible loops are in this circuit? So the circuit that I'm thinking about is that I'm looking at a circuit that has 3 loops like this. Well, let's count the loops. So let's imagine that I have this. So let's start color coding these loops, just like we did with the nodes. So you can see that there's a possible path that looks like this. I'm going to call that 1. I'm going to call this loop 2. And then this one I could also include, so that's 3 possible loops. But I could have taken other loops. In fact, I'm going to copy this because it's going to be useful to have, because I'm going to repeat the process here. So there's another loop. This can be a possible loop. So now that's 4. Or here's another possible loop, would be the other side of this guy, which then tells me that I have this loop right here. And that will be the 5th loop. And then I could have even another possible loop, which then comes in and it looks like this. So that would be 6 possible loops. There are 6 possible loops. However, there are only 3 independent loops. And that becomes important. So now let's go in and look at Kirchhoff's voltage law. So Kirchhoff's voltage law, we lovingly called KVL, and this guy is about counting loops. What are the independent loops? So Kirchhoff's current voltage law says that the sum of voltage drops around any closed loop is 0. In other words, if I sum all of the voltages around a loop, they have to be equal to 0, where the sign convention becomes super important. And this is where we run into problems with physics 4B and how it's taught. So what I'm seeing here is that I'm going to draw 2 elements. And so if I'm going to copy this guy right here. And what ends up happening is that we typically want to choose the path so that we imagine that the path is the direction of current flow. So if I look at this thing, then what do I see here? What I see here is that I'm going to see something like this here. I'm going to have a voltage drop across an element, which I'm going to call V here. And that voltage, like I said before, is typically positive. That's only assuming your direction of path. So in this situation, if our path, which we think is typically the current, we're saying that if the path is coming this way, then we say that this voltage here is positive. However, if I look at the voltage, if the voltage is still the same polarity that is, but now the current comes in this direction, or the path comes in this direction, then we say that there is a negative sign on that voltage. So again, we're following the sign convention where depends on how it enters the node. So then, once again, this sign convention is opposite to physics 4B's way. I happen to disagree with it. The physics sign convention actually makes circuit problems harder to track signs.